The Very Large Telescope is a powerhouse. Although you might be forgiven for looking forward to the completion of the Extremely Large Telescope in 2025, few telescopes today can compete with the sheer productive output of its predecessor, the VLT. The number of scientific papers this telescope contributes to averages out at more than one a day, nearly 600 in 2019, dwarfing the competition from all other land-based telescopes. And even once newer, larger telescopes with their 30-meter plus mirrors start to come online, the VLT will still have its niche. Thanks to a little trick up its sleeve, its 8 telescopes can combine into a virtual mirror with an effective diameter of 200 meters, giving it punching power far above its weight. So, what is the Very Large Telescope? What contributions has it made to science? I'm Alex McColgan, and you're watching Astrum. Join with me today as we investigate how this incredible piece of engineering works and see its discoveries behind black holes, neutron stars, and even how it helped prove general relativity. The Very Large Telescope finished construction in the year 2000, although that sentence is a little misleading on 2 different levels. The first is that the VLT isn't just a single mirror telescope. A misleading name then? Maybe. Let's see why it's still only considered one telescope. Initial designs had it as a limited array of 4 behemoth telescopes, 25 meters tall each, with mirrors stretching 8.2 meters across. These were called unit telescopes, and they could work independently at studying the stars. Each one is capable of an angular resolution of 50 milliarc seconds, which is good enough to see details smaller than a DVD on the International Space Station. The second level is that the VLT is constantly evolving. In some sense, it is not finished even now. In 2004 and 2007, a total of 4 new auxiliary telescopes were added to the VLT's array. Each of these auxiliaries has a smaller mirror, only 1.8 meters across. Additional instruments have been routinely added over the years, some as recently as 2018. There are 16 currently in operation, ranging from spectrometers to infrared images, with more to come in the future, such as Foremost, which is an upgrade to the Vista telescope instrument that is also part of the VLT site. Maintaining such a massive array can be difficult. VLT mirrors are exposed to the open air each night. The Atacama Desert in northern Chile, where it's situated, may be ideally suited for observations. It hasn't rained there since records began, but dust can sometimes blow in. Every 18 months, the mirrors must be delicately washed with chemicals designed to remove their aluminium coating, and then a new one is applied. This process does not need very much aluminium. Only about 12 grams is used to coat an entire 8-meter mirror, less than the amount used in a drinks can. This is because the aluminium is coated on the mirror about 80 nanometers thick. Each unit telescope is a pristine feat of engineering. The 430-ton structures are each about the weight of a jumbo jet, and yet they're so perfectly balanced on their hydrostatic oil film bearings that they can be rotated by hand. The mirrors are so precise, if you scale them up to the size of the whole Earth, the imperfections on them would be smaller than a pebble. But the truly impressive feats are still to come. As powerful as each unit telescope is on its own, it is when they work together that they can act as one telescope. Let's talk about the telescope's technique known as interferometry. Light travels in waves, and when you combine 2 waves just right, their peaks can amplify each other. Underneath the VLT, there are a series of tunnels lined with mirrors in complex configurations. Light from the various telescopes is fed into them. They are placed with accuracy down to a fraction of a wavelength to ensure the light enters in just the right phase so that everything lines up. In this way, a greater resolution of detail can be gained. An individual unit telescope can see objects that are 4 billion times fainter than what you can see with the naked eye. When interferometry is brought to bear, this becomes 25 times more effective. It should be noted that the amplified waves of light do have some drawbacks. Light, as it bounces around all these mirrors, can get lost. The process is not very efficient. As a result, the object the VLT is looking at needs to be quite bright to begin with. Secondly, interferometry does not naturally create full images, instead merely picking out certain details and features of what is visible in what are called fringes. However, this is often enough for astronomers' purposes. And if a more detailed image is required, the VLT's observational data can be processed into crisper, full images. It just takes more time and processing power. The VLT's effective 200-meter diameter virtual mirror provides excellent resolution, but that's not to say that it's able to pick up the same quantity of light as even the 30-meter mirrors. Obviously, there is a lot of empty space between the units that is not covered by mirrors. They are not picking up any light. But what it does perceive is revolutionary, ranging from the beautiful, like this eye-catching look at galaxy NGC 1398, to the groundbreaking, like this first ever image taken of an exoplanet. VLT is often on the forefront of discovery. Exoplanets are normally only seen through the absorption of light traveling through their atmospheres, or the slight dimming of any stars they pass in front of. It's rare to see an actual photograph of one, and yet in 2004 the VLT captured this image of 2M1207b, a Jupiter-like planet that is located 230 light-years away from us in the Hydra constellation. This image was taken with the aid of NACO, the Nasmyth Adaptive Optics System, which has since been replaced by the more advanced optics system known as NAOMI, the new Adaptive Optics Module for Interferometry, which, according to the ESO website, is putting the VLT's interferometer on steroids. It's worth noting, adaptive optics is a vital part of ground-based telescopes. Movement in the atmosphere can cause distortions in the light arriving at the telescope from distant stars. This can make it much harder to make out detail, and is the main advantage of space-based telescopes over ground-based ones. In space, you don't have to compete with the atmosphere between you and the object you're observing. However, the VLT's adaptive optics showcase an ingenious solution to this problem. By using guide stars, or lasers if no suitable star can be found, the VLT can track the distortion taking place as a result of the atmosphere by seeing how the light from these guides differs from what it should be. Then, using actuators under the mirrors of the unit telescopes themselves, the VLT causes tiny distortions in real time in the mirror to counteract the distortion in the air. This can negate much of the negative effects of the atmosphere, granting the VLT a much better look at the universe. So, let's talk about some of the VLT's discoveries. With so much data to choose from, it's really about picking my favorites. The VLT has looked at the aftermath of colliding neutron stars, detecting for the first time the freshly made heavy element strontium, an element used in fireworks. It has measured the temperature of the distant universe by detecting carbon monoxide atoms, confirming that 11 billion years ago, space was slightly warmer than it is now, minus 264 degrees Celsius versus minus 270 degrees Celsius. So admittedly, still quite chilly. But perhaps the most exciting discoveries of the VLT was its role in helping prove the theory of general relativity, which earned Reinhard Genzel the Nobel Prize for Physics in 2020, as well as confirming the existence of the monstrous black hole at the center of our galaxy. Einstein's theory of relativity had long predicted the existence of black holes, as shown by Karl Schwarzschild in 1619. For decades though, scientists wondered whether these universe-warping objects actually existed. A mathematical physicist named Roger Penrose went on to prove in his 1965 paper, Gravitational Collapse and Space-Time Singularities, that black holes were not just mathematical artifacts in Einstein's theory, but concrete certainties. It was inevitable that they could and would form. But still, it took until the turn of the millennium before the first black hole was confirmed. During this time, scientists began to suspect that there was one such black hole at the center of our own galaxy. Radio signals had been detected coming from the center of Sagittarius, 25,640 light-years away, as far back as 1931. In 1971, two radio astronomers, Bruce Ballack and Robert Brown, noticed a bright, compact object at our galaxy center that gained the name Sagittarius A star. But telescopes were not powerful enough to truly peer into the heart of Sagittarius A star to confirm what it was. This changed with Andrea Ghez and Reinhard Genzel in the 1990s. Through detailed observations that span nearly 30 years, each astronomer began to map out the motion of stars in the center of Sagittarius to see how they interacted with Sagittarius A star. General relativity predicted rapid movement of any star moving past a black hole. However, it also predicted precession, a change in the orbital path over time in the direction of the star's motion. Rather than looking like a circle or an ellipse, a star showing such precession would travel the path of a rosette through space. But this would require detailed evaluation of the stars around Sagittarius A star for multiple orbits, and each orbit could last up to 16 years. So, decades of observation were needed to confirm Einstein's theory. And fortunately, telescopes like the VLT were by this point available for use. Genzel's team made use of the VLT to watch the motion of the stars around Sagittarius A star, while Ghez made use of the Keck Observatory in Hawaii to do the same. Together, they were able to confirm this precession was indeed taking place. As further evidence, in 2018, the VLT observed star S2 traveling around Sagittarius A star at 7,650 kilometers a second, or 2.55% the speed of light, exactly in line with the speeds Einstein had predicted. This finally confirmed Sagittarius A star's identity as a supermassive black hole. Thus, in 2020, Ghez and Genzel both received the Nobel Prize of Physics for the discovery of a supermassive compact object at the center of our galaxy. And Roger Penrose, who had first proved mathematically that black holes inevitably arose out of Einstein's theories, received a Nobel Prize for the same. So, there you have it. The VLT has been massively influential up until this point, providing data for countless scientific papers and placing itself as one of the most productive telescopes mankind has yet produced. But going forward, in an era where extremely large telescopes begin to be more common, and as telescopes like the James Webb Space Telescope orbit in our skies, the VLT will need to up its game to stay relevant. It will need to evolve, with its instruments continuing to be updated and modified. The VLT still has the potential for years more of valuable contribution to the scientific community. Astronomers will need to think carefully about how this is best achieved. But it should not be too difficult. The VLT is a powerhouse. I'm certain it will continue to find its niche for years to come. So, were you already familiar with the VLT? Would you like to hear more about VLT and its discoveries? Let me know in the comments below. The James Webb Space Telescope. Named after the NASA administrator who oversaw the Apollo moon landings, this space behemoth is the largest, most powerful, and most complex space telescope ever built. It has been hailed as the successor of Hubble, which itself was instrumental in expanding our understanding of the universe over the last few decades. It has undergone major redesigns, cost $9.7 billion to build, and has taken 25 years to fully develop, construct, and test. There were moments in its decades-long construction where it was very nearly cancelled completely. And yet, with the aid of scientists from several nations around the world, it has overcome hurdle after hurdle. But for all this, it will only last in space for a maximum of 10 years. Why have scientists undertaken the construction of this telescope? Why put all this time, money and effort into building something that will be, relatively speaking, so short-lived? The answer is because this telescope, in a way unlike any before it, will allow us to peer through time to the beginnings of the universe itself. I'm Alex McColgan and you're watching Astrum. Join with me today as we explore how this incredible spacecraft will allow scientists to pull back the curtain on the first galaxies to come into existence after the Big Bang. Together we will discover the science and engineering that went into it, as well as the challenges it faced. Because this truly will be a spacecraft that will help us access clues to the universe's origins like no other. The James Webb Space Telescope first began in 1996. NASA at that time had for years been considering a Next Generation Space Telescope, or NGST, to help them find the data they desired, and the original plan was to make an 8-meter aperture telescope that would cost approximately $500 million. However, as time went on, decision makers realized that far more resources would be needed to achieve their aims. But what exactly were their aims? Well, the NGST was to be an infrared telescope. Hubble had been functioning since 1990, but its primary range was the visible light and ultraviolet light spectrums. Although it had some infrared detection capability, this was somewhat limited. And why do scientists want a powerful infrared telescope? Well, this comes down to some fundamental facts about the universe itself. Scientists believe the universe as we know it has existed for roughly 13.8 billion years. How it all began is a fascinating question, and one that many have theorized over. Current mainstream theories revolve around the idea of a Big Bang, where all matter existed in a space so small it was effectively zero. Atoms did not even exist at that stage, they would have been too large. Suddenly, everything expanded outwards at once. Matter began to coalesce into atoms, and then dust, then stars and planets, and the universe has expanded and cooled ever since. But wouldn't it be helpful to be able to look back and see for ourselves those first moments of creation, or the formation of those first galaxies? That might give us insights into exactly how all of it happened. The James Webb Space Telescope will either provide evidence for the Big Bang, or completely change our theories, thanks to the way light travels. To a point at least. While light is blindingly fast, it's not instantaneous. There is a tiny time delay between when light is emitted and when we see it. Photons, or particles of light, travel at a constant rate, 299,792,458 meters per second exactly. Our sun sits at a point 148 million kilometers from us. This means that it takes approximately 500 seconds for light to travel from it to us. So what you see in the sky right now is not the sun as it is, but the sun as it was 8 minutes and 20 seconds ago. This time delay becomes severe even when you consider things that are relatively close to us. The next nearest star, Proxima Centauri, is so distant from Earth that it takes 4 years for its light to reach us. All of this means that for objects that are further and further away from us, we would see it as it was further and further back in time. If there was an object sufficiently far away, we would see it as it was 13.8 billion years ago, near the origin of the universe. And fortunately, as some speculate, we exist in an infinite universe, so such faraway objects should in fact exist. With the James Webb Space Telescope, we hope to be able to see them. But why does the James Webb Space Telescope view in the infrared? Well, one reason is that infrared light tends to punch through clouds of cosmic matter better, allowing us to see past otherwise opaque gas clouds, to see what lies on the other side. But the main reason, and the one that is relevant to seeing those early galaxies, is because of a second quirk of the universe, the fact that space is expanding. For reasons we don't fully understand, but which scientists currently theorize are the result of dark energy, everything in the universe is moving away from everything else constantly. As a star moves away from us, the light from it is stretched in a process known as the Doppler effect. And because the wavelength of light is the part that defines what color we see, as light stretches, it shifts further and further towards the red half of the spectrum. But this expansion isn't constant. Scientists have observed that the further something is away from us, the faster it is expanding away from us too. This means that light from the furthest away galaxies have shifted so far into the red that it has gone beyond it, into infrared frequencies. Hubble was not fully designed to detect these frequencies. The James Webb Space Telescope is. James Webb's receptors can detect light at frequencies from 0.6 micrometers to 28.5 micrometers long. Interestingly, this means that it actually can't see all visible light frequencies. It can see red and a large amount of orange frequencies, but nothing beyond yellow. Its focus lies in the infrared frequencies. In this way, to say that the James Webb Space Telescope is a replacement for Hubble is factually incorrect. At NASA, they prefer to say that James Webb supports and complements Hubble. Each will focus on frequencies of light that the other does not see so clearly. Besides which, as Hubble could potentially last until 2040, it's likely that it will outlast the James Webb Space Telescope too, which would make James Webb an odd replacement. Still, to see these infrared rays from such distant sources is a huge challenge. If you and a friend each held a candle on a clear night and walked away from each other, it wouldn't be too long before your candle started to look dimmer to the other person. This is because of the inverse square law, where light photons spread out with distance. Plus, light tends to scatter when it passes through matter. And although space is extremely empty, there's enough particles of dust floating around that over the vast distances of space, objects that are far away get more difficult to see. To combat this, the James Webb Space Telescope houses a gold-plated beryllium mirror that is 6.5 meters in diameter. This makes its surface area 6 times larger than that of Hubble's mirror. This larger mirror is designed to catch more light from distant sources before focusing it back into the telescope's instruments, allowing them to pick up fainter traces of radiation. Furthermore, as the name suggests, the James Webb Space Telescope is a space mirror. Being in space means that the telescope does not have to contend with the Earth's atmosphere, which can diffract and distort light waves that pass through it. The vacuum of space provides a much clearer view, allowing James Webb to find those tiny diffuse infrared waves much more easily. James Webb will be orbiting the Earth in a position known as the L2 Lagrange point. This position in space is technically not a true orbit, but exists 1.5 million kilometers from the Earth at the point furthest away from the Sun. For point of reference, the Moon is 384,400 kilometers from the Earth, so this is much further out. Due to the way the Earth's gravity interacts with the Sun's, this point of space is gravitationally stable, making it easier for an object to hover there with minimal effort. This makes it an ideal viewing station for an orbital telescope. One spacecraft was sent there already, the Planck Space Observatory. The distance from Earth is far enough away that the James Webb Space Telescope does not have to contend with any radiation bouncing off the Earth or the Moon, but it is also close enough that it can send signals back to Earth telling us what it sees. Naturally, at this position, it will be very difficult for us to visit the James Webb Space Telescope. So, although James Webb was designed with a docking ring, it is currently planned that there will be no missions to James Webb to service or replace its parts once it's up there. Although it needs minimal effort to maintain its position, minimal is not zero. James Webb has enough fuel to maintain its position for at least 5 years, and at most 10. After that, it will decay from its orbit and will no longer function. It has a guaranteed expiration date. One final benefit of this position, however, is the temperature. Because heat travels in infrared waves, the heat generated by the telescope's own parts could potentially blind its own sensors if left unchecked. However, thanks to its position in space, James Webb will be able to cool itself to temperatures of -223 degrees Celsius. This is also aided by its solar shield. You have no doubt noticed the large silver canvas at the bottom of the satellite. This 5-layered shield is the size of a tennis court and is designed to point in the direction of the Sun, Earth and Moon to block heat coming from them. With that last fact, you may have begun to realize the scale of this satellite. It is vast, roughly 20 meters by 14 meters, and weighing almost 6,500 kilograms. This raises a question: how are they going to get this telescope into orbit? Well, that is explained by one of the most, frankly, astounding engineering aspects of this telescope: its capacity to fold up and unfold. The Ariane 5 rocket that will carry James Webb into orbit has a 5-meter diameter, but this is not sufficient to fit the James Webb Space Telescope. As such, James Webb has been designed so that its mirror can fold in, as can its solar shield, reducing its total dimensions while it is in the rocket. Once it has been launched, and while it is traversing space to its Lagrange point, the James Webb Space Telescope will begin gradually unfurling in a delicate ballet. Arms will unfurl, shields will unspool. The hexagons of the mirror will rotate into position, and then align themselves with the aid of tiny motors that are perfectly flush with each other, all to allow it to go about its incredibly delicate business of gathering radiation from the dimmest lights in the sky. Mastering this process of getting such a sensitive device into orbit without something breaking is the reason James Webb has taken so long to build. Remember, once launched, there is no chance of going up there and fixing it. If something broke during deployment, it could well spell the end of the entire mission, wasting over 2 decades of work and $9.7 billion. In 2005, just a few years before the initial intended launch date, the entire project underwent a fundamental redesign. Everything was checked and double-checked by review boards. In 2018, the project was further delayed when a test of deploying the solar shield ended up with it ripping. A review of what went wrong found an additional 344 potential single-point failures, any one of which breaking would mean that the entire thing would no longer work. When costs started rising in 2011, the American Congress moved to reduce NASA's budget of a way of cancelling James Webb. However, the public backlash in support of the project ultimately led them to reverse their decision. James Webb was built by NASA in cooperation with the European Space Agency and the Canadian Space Agency. It has been delayed over 13 times. Its project costs have increased from $500 million to $9.7 billion. But finally, very soon, it will be here. Its mission to peer into the heart of space and uncover the mysteries of the formation of the first galaxies, stars and planets will finally begin. You can bet that when it launches from the European spaceport in French Guiana, there will be plenty of people waiting for news of a successful launch with bated breath. And you can also bet that once it's in the sky, scientists will be fighting tooth and nail to get a chance to look through it and to discover what wonders it sees. So, good luck for the launch and the deployment to all the teams involved with this. If it works, this instrument will be the biggest thing for space science for potentially decades to come. We are all, in my opinion, rightfully excited about the James Webb Space Telescope launch in 2021. Such a powerful space telescope will allow us to see things extremely far away with a heretofore unprecedented fidelity. However, there's another telescope also due to be completed in 2021 that no one is talking about, even though it is the top-ranked ground-based project in the Astrophysics Decadal Survey of 2010. What is it, and what does it do? Why do astronomers consider this project to be quite so important? I'm Alex McColgan, and you're watching Astrum, and together we will go through everything you could want to know about the Vera C. Rubin Observatory. Very interestingly, the Rubin Observatory is not connected to a major space agency. Funding has actually come from the United States National Science Foundation and Department of Energy, and the management is overseen by the Association of Universities for Research in Astronomy. It's also being built in Chile, the location of many ESO telescopes, but these aren't connected. Chile just so happens to be an amazing place for a ground-based telescope, with its high mountain range and little to no cloud cover. This is important because the Rubin Observatory's primary goal is to survey the entire visible sky every few days. It will do this with its incredible 8.4 meter mirror and 3.2 gigapixel camera.
Just to give you some perspective, the mirror is the width of a tennis court, and the camera is the largest ever constructed. It's 3 meters long and about 1.6 meters wide. The lens of the camera allows the telescope to view 3.5 degrees of the sky at the same time. This is a really big area of the sky. The moon and the sun are only about half a degree across. This camera is also capable of viewing from the near ultraviolet to the near infrared wavelengths. It does this with a robotic arm that changes filters placed in front of the sensors. You see, certain objects or events that happen in our sky are brighter in specific wavelengths of light. But what is the Rubin observatory designed to look at? Because it's conducting a sky survey, it's looking out for pretty much everything. Its particular science goals are to look out for evidence of dark matter and dark energy, mapping small objects in the solar system, particularly near-Earth asteroids as well as larger objects in the Kuiper belt, detecting supernovae in our galaxy and beyond, gamma-ray bursts, quasar variability, gravitational lensing, and lastly, it will map the stars in the Milky Way. There have been plenty of sky surveys in the past. Notable mentions are the impressive works done with Gaia, Pan-STARRS, DESI, and the Sloan digital surveys. These have been extremely useful in mapping our surroundings with extreme accuracy, cataloguing galaxies, stars, and asteroids. However, the Rubin Observatory will be able to see a lot more than any of these previous surveys. At the end of 10 years of operation, it is expected that data from the Rubin Observatory will allow us to catalogue 10 to 100 times more asteroids larger than 140 meters than what we currently know about, or around 62% of what probably exists in a near-Earth orbit. With its wide field of view, gravitational wave events that are detected by LIGO might be visible in an image taken by the Rubin Observatory. LIGO is also predominantly a National Science Foundation project, a very special type of observatory that uses mirrors placed 4 kilometers apart, which are capable of detecting a change less than 1/10,000th the charge diameter of a proton. These changes can occur as gravitational waves pass through the facility. The sources of these waves come from really big events, like neutron stars or black holes colliding, which creates a ripple in space-time that propagates outwards from the location of the event. These events are usually so far away that by the time they reach us, we need a sensitive observatory like LIGO to even detect them. Gravitational waves travel at the speed of light, so if we detect gravitational waves, there should also be light coming from the source. With such events, we only roughly know the direction of where it could have come from due to the way we detect events with LIGO. So to visually see it with a telescope, time is spent scanning the sky, by which point we may well have missed it. However, if you have a telescope capable of seeing a big chunk of the sky at the same time with a super high resolution camera, you can take a lot of photos and search the data later to try and locate the event and see if it was visible. So, how will it be able to achieve these science goals? The telescope will typically observe a section of the sky for 15 seconds. A 15-second exposure is a compromise between being able to see faint objects like distant stars and moving objects like asteroids. If you have much more of an exposure, you may see more faint objects, but streaks across the image will ruin the shots from the moving objects. In order to eliminate the noise from cosmic rays hitting the camera sensor, 2 images of the same region will always be taken and can then be merged. The camera's images will be so large that a year's worth of data will come to about 1.28 petabytes. And because the observatory is located in Chile and the data processing facility is in the States, a special 100 gigabit per second internet connection had to be specially built between the 2 locations. Unfortunately though, there is a pretty major problem coming up that the designers may not have fully envisaged when in the planning and early construction phases of this project. Any guesses to what would affect a highly sensitive ground-based telescope that wasn't such an issue 10 years ago? Not pollution, not light from cities, but actually the tens of thousands of CUBE satellites currently being launched into space from the likes of SpaceX and Amazon. If a satellite passes through an image, it will ruin the exposure because it is so bright compared to the dimmest objects the telescope is looking for. As a result, SpaceX have committed to painting their future satellites black, or send them up with a kind of sunshade to reduce how bright they are, but this certainly won't negate the problem. And in reality, low Earth orbit is only going to get busier. This puts a serious dampener on the future of highly sensitive ground-based telescopes. In reality, the serious issue here is that there are currently no internationally agreed regulations about what can be put into low Earth orbit. It's the Wild West right now. And that's not to mention how this increases the chances of Kessler syndrome, which I have already done a video about here if you want to know more. But all in all, this is a very exciting project. And even with these obstacles, I'm sure it will acquire a wealth of valuable data. Perhaps it will even witness events we have never even conceived possible before. So there we have it, an insight into the most exciting telescope that hopefully more people will begin talking about. While the James Webb Space Telescope is still capturing headlines in media for being the most exciting future telescope project, there's another ground-based telescope that hasn't had as much attention that's under construction right now, and it will make the James Webb Space Telescope look like a minnow in comparison. Introducing ESO's Extremely Large Telescope, or the ELT. So what is it, and what does it hope to achieve, and how does it compare to the many other telescope missions out there? I'm Alex McColgan, and you're watching Astrum, and together we will explore the ELT and see why it may be the most exciting telescope project of the decade. The ELT is a project of ESO, or the European Southern Observatory. I must say, ESO is an amazing organization, and it is a prolific gatherer of data due to its many telescopes and instruments. Although it is a European project, the observatories themselves are based in the Atacama Desert in Chile. This region was picked due to the elevation of the sites, meaning there is less atmosphere between the telescope and space, and also because some sections of this desert haven't seen rainfall since records began. As the sky is generally clear, it makes this region perfect for astronomical observations. While all the individual telescopes of ESO are too numerous to mention, I'll mention a couple of notable projects. One is ALMA, which is the best observatory for looking at the cold universe, like molecular clouds and dust. It consists of 66 antennas, all working in tandem together. Another is the VLT, or the Very Large Telescope, which, unsurprisingly, will end up being the ELT's predecessor. It comprises of 4 8.2 meter telescopes and 4 additional 1.8 meter auxiliary telescopes. They can all work in tandem or separately, depending on the requirements. When they work together, they can achieve an exceptionally high angular resolution, or in other words, they can see details 25 times fainter compared to operating separately. These telescopes are currently the flagships of ESO, and they are the most advanced optical instruments in the world. Now, I show you these other projects because to truly appreciate how ambitious the ELT is, you need to compare it to the next best projects we have at the moment. So let's start with its size. Remembering that the VLT has 8.2 meter wide mirrors, the ELT's primary mirror is going to be an incredible 39.3 meters across, with a surface area of 978 meters squared. A telescope of this size means the main mirror is going to be segmented, with 798 segments in all. With the main mirror being segmented, it means individual segments can be replaced and cleaned. Together, the ELT's main mirror will collect 100 million times more light than the human eye. and around 26 times more than a VLT unit telescope. Due to the size of the main mirror, several other mirrors are necessary to condense all that light into the science instrument. That means there will be a secondary, tertiary, fourth and fifth mirror before the light even hits the instrument. These smaller mirrors will also be special. The secondary mirror will be the largest convex mirror ever produced. The fourth mirror will be the largest adaptive mirror ever produced, with 8,000 actuators, so that the surface can be adjusted at very high time frequencies. It will be adjustable to counter the distortions in the image caused by the Earth's atmosphere, and also from wind vibrating the main mirror, all in real time. Now, unsurprisingly, with all the glass and the need for sturdy supports, this structure is going to be really heavy, 3,700 tons, meaning it's going to need a behemoth of a dome to support it and rotate it. Combine this with the fact that the site is based in a desert that is prone to earthquakes, and these required specifications make the dome almost as ambitious as the telescope itself. Once completed, it will end up being 80 meters high and 88 meters in diameter. To give you some perspective, here it is compared to the Colosseum in Rome or Manchester City's Etihad Stadium. To protect the mirrors during the day, these doors can close, and there are wind shields which reduce the amount of wind and sand reaching the mirrors. The whole design was tested in a wind tunnel to ensure as much wind as possible is directed around the structure. While a lot has been done to reduce the weight as much as possible, the total weight of the dome and telescope still comes in at 6,100 tons. The dome itself is also protected against earthquakes, as it is built on top of massive shock absorbers, which will protect the sensitive equipment from the regular, strong earthquakes Chile experiences. Now, if you've ever tried photographing the night sky before, you will know that unless you have an automatic tracker, you are going to get some blurry images if you do a long exposure. And the ELT is no different. One of the big design challenges of the ELT is not only being able to rotate the telescope around, but also up and down with as few vibrations as possible to allow it to get as long of an exposure as it needs. To achieve this, the moving part of the dome will rest on 36 stationary trolleys with wheels on the top. The upper dome will have tracks where the wheels fit into. These trolleys and wheels have been specially designed to produce the minimum of vibrations possible. Next is the Alt-Az mount, the machinery that controls the altitude, or the up and down, and the azimuth, or the rotation of the telescope. Keeping 3,700 tons steady and without buckling means that this has to be an impressive mount indeed. The whole lower pier rests on 3 circular tracks of hydrostatic ball bearings, so accurately constructed that their positioning will be correct, aligned to a precision of just a few tenths of a millimeter over their full diameter. The altitude control section will rest on top of the pier and is the structure holding the mirror itself. There are 2 semicircular plates on either side of this structure, resting on top of a cradle of hydrostatic pads. Hydrostatic bearings and pads basically means that the structure is resting on a thick oil layer, which produces very low friction and can also provide a vibration absorbing effect, helpful to further reduce vibrations caused by the equipment and earthquakes. The design of this telescope gets even more impressive when you see how they deal with the distortions caused in the Earth's atmosphere, and also the variations caused by wind and temperature changes. The design problem with ground-based telescopes is that you have an atmosphere above you that moves and wobbles incoming light photons, so to speak. This puts a hard limit on how much detail you can see in space. Not to mention the vibrations on the mirror caused by the slightest wind, or the tiny expansion or contraction of the structure caused by temperature changes, meaning the segmented mirrors go out of alignment ever so slightly. As I mentioned, engineers have tried to reduce these problems as much as possible. By building it in the Andes at an altitude of 3,000 meters, there is less atmosphere between the telescope and space compared to sea level. Also, with the windbreaker and powerful ventilation and air conditioning, wind and temperature changes should be kept to a minimum. But this isn't enough to get the quality of images ESO are hoping for. This hasn't deterred the brightest minds in astronomy and engineering, as they have come up with a process called adaptive optics. As I mentioned, the fourth mirror on the telescope will be a hugely impressive adaptive mirror. A computer will keep track of turbulence in the atmosphere by observing the movement of guide stars, or even artificial stars created by these powerful lasers, and send corrections to the fourth mirror's 8,000 actuators to distort the mirror so that light reflecting off it hits the fifth mirror almost as if the atmosphere was not there. If you look up at stars and notice that they twinkle, this is the atmosphere causing the starlight to wobble. Twinkling happens rapidly, and the distorted mirror has to keep up with those changes in real time. The computer will also keep track of the primary mirror segments to make sure they stay aligned too. Adaptive optics will mean images taken by the ELT can be sharper than space telescopes due to its much bigger mirror. While adaptive optics don't completely eliminate atmospheric distortions, the fact its mirror is so big means it will easily keep up with or even exceed the James Webb Space Telescope in some observations. So, where does this light end up? Well, into a variety of instruments, all designed to do something slightly different. Some of the highlights include 3 powerful spectrographs and 2 cameras that will put the one on the James Webb Space Telescope to shame. Here you can see an expected spatial resolution difference between the Hubble Space Telescope, the James Webb Space Telescope, and the ELT. These cameras will work effectively from the visible light spectrum to the mid-infrared. Both cameras will be housed in cryostats to keep them cool, so the infrared light won't be affected by the heat coming off the camera itself. Because James Webb will be in space, it can better detect the dimmest of objects emitting infrared light, like galaxies billions of light years away. However, the ELT will still be useful for looking at nearer objects, especially objects obscured by dust. Cool dust becomes more or less invisible in infrared frequencies of light, meaning the ELT will have the best capabilities for seeing through these shrouds in our galaxy. And what science do they hope to collect with these instruments? The design and technology of it are impressive enough, but what will it see? Well, this is the most exciting aspect of the ELT. One of the primary missions is to use the cameras and spectrographs to examine known exoplanets more closely. One camera will come equipped with a coronagraph, meaning it will be able to block light coming from a target star so that it can better view dim, orbiting exoplanets without the starlight washing out the image. Don't expect images like we have of planets in our own solar system. However, simply confirming their existence will prove our exoplanet hunting methods are effective. Not only that, but the spectrographs will analyze the light coming from these exoplanets to determine their composition. Scientists will especially look out for clues that these planets can sustain life. The obvious substance to look out for is water, but there are plenty of other markers too if that life were to be similar to ours, like oxygen, methane, nitrous oxide, and chloromethane. Talking of planets, ELT will examine planets in our own solar system. Half the planets in our solar system do not have their own dedicated mission, so the ELT will be the next best observatory we have to keep track of them. Scientists will also observe objects normally hidden by dust, like protostars and old stars, to give us a better understanding of how stars form and their evolution over time. And talking of stars, it will also peer past the dust obscuring the most fascinating part of our galaxy, the region directly around the supermassive black hole in the galaxy center. We know of 40 stars that orbit the supermassive black hole right now, but we expect to be able to detect a lot more with the increased spatial resolution provided by the ELT. This is a really interesting section of space for astronomers, as the supermassive black hole warps space-time dramatically there, and there is still a lot we have yet to understand about an environment like this one. The ELT will also look towards the centers of nearby galaxies to see how they compare. The last thing it will investigate further, and I know some people hate to hear it, is the nature of dark matter and dark energy. Under our current understanding of physics, there is a force countering gravity and pushing everything apart, currently known as dark energy. At small distances, gravity overcomes this expansion of the universe, but over millions of light years, the universe is expanding rapidly. I've done a video about it here if you want to know more. Additionally, galaxies have more gravity than they should, meaning they rotate differently than we would expect. This extra gravity is blamed on dark matter. Again, check out this video I made about that here. To quote ESO, what dark matter and dark energy suggests is that our theories of cosmology and particle physics are incomplete or possibly incorrect, and that new physics is out there waiting to be discovered. A key task for the next generation of astrophysical facilities is to search for, identify, and ultimately characterize this new physics. With the ability to better examine the halos surrounding galaxies, to characterize dark matter, and, in tandem with the James Webb Space Telescope, see the universe expand in real time, which is something that hasn't been able to be done before, the ELT will provide unique contributions towards deciding whether general relativity or a modified theory best describes the expansion of the universe, including testing the behavior of gravity in unexplored regions, as well as mapping the expansion history of the universe. So, data from this telescope could provide us with a new understanding of gravity and physics as a whole. Alright, that just about wraps up everything here. Sadly, we are going to have to wait 4 years for this project to finish construction, but if you are already excited for the James Webb Space Telescope, just wait until this is finished. Although, with any luck, the James Webb Space Telescope will hopefully launch this year, everything will deploy smoothly, and it will soon be sending us fantastic data that we can enjoy in the meantime. Back in April, NASA announced that they would cease operations of the infrared telescope known as SOFIA. If you have never heard of this telescope, you're in for a surprise. SOFIA is a fascinating example of NASA trying something quite different, and although it did not prove to be as effective as they might have wanted, the incredible engineering that went into it and the things it discovered make this telescope an important part of space history. But what is SOFIA? Well, it's not a ground-based telescope, neither is it a satellite-based one. SOFIA is a telescope that sticks out the side of an aeroplane. I'm Alex McColgan and you're watching Astrum. Today, as we near the end of SOFIA's operation, it seemed appropriate to look back on the history of this quirky telescope and learn about the design choices that went into it and what discoveries it made, and ultimately ask, was it worth it? I don't know about you, but when I first saw SOFIA, or the Stratospheric Observatory for Infrared Astronomy, my mind was immediately buzzing with questions. Most pressingly, why an aeroplane? Why not a satellite like Hubble, or James Webb, or maybe something ground-based? You might guess that the modified Boeing 747 that houses the telescope is possibly cheaper than launching a satellite into orbit, and you'd be partially right, but not as right as you might think. SOFIA was expensive to build and expensive to operate. To make a few comparisons, while it cost NASA $1.5 billion to build and launch the Hubble telescope, SOFIA still cost $1 billion in an 80-20 collaboration with German scientists. Not that far off. And the $85 million a year required to keep it going isn't that much less than Hubble's ongoing maintenance costs. In fact, the high cost of SOFIA was cited by NASA as the main reason for discontinuing it. You might wonder whether it's more fuel efficient than a rocket. Rockets certainly are fuel guzzlers. The SpaceX rocket Falcon 9 uses over 75,000 gallons of propellant, a mixture of liquid oxygen and kerosene. This fuel top-up for the reusable rockets costs $200,000 to $300,000, but SOFIA's Boeing 747 is actually comparable. Its tank fits around 60,000 gallons of a different type of kerosene, which also costs around $200,000 to fill up.
and given the fact that it flies 3 times a week for 10 hours at a time, burning through about half a tank in one run, all in all, that's a lot of expensive fuel used. But it does have some advantages. The main benefit of space satellites is that they get above the Earth's atmosphere. Air molecules refract light, which means that if you can get above the atmosphere, you can get much clearer, crisper images. SOFIA is able to fly above 80 to 90% of the atmosphere, so it shares this advantage with a space satellite. But unlike a satellite orbiting the planet, at the end of a flight, SOFIA can come down again. This makes it much easier to maintain, and also to swap out its scientific equipment, giving SOFIA much greater flexibility in the sorts of things it can detect. This has proved invaluable in SOFIA's 8 years of life, as we'll see later. Still, I don't think this is the true reason SOFIA is an aeroplane-based satellite. To understand the real reason, it's important to know a little bit about the history of flying satellites. For SOFIA was not the first. Flying observatories actually date back to 1957 with the balloon Stratoscope 1. The idea was simple: put a telescope on a balloon, send it 25 kilometers into the air, and have it take photographs of the sun. However, plane-based telescopes wouldn't come along until the solar eclipse of 1965. Phenomena like solar eclipses are very location-based. Depending on where you are in the world, you will get a better or worse view of a solar eclipse. As the moon travels between the Earth and the sun, its shadow travels across the continents, meaning some get to see the full eclipse, while others only see a partial eclipse, or none at all. So NASA decided to put a telescope on a plane to chase the solar eclipse across the globe, thus giving it the best view of this phenomenon. This was something that only a telescope on an aeroplane could do. Neither a fixed-in-place ground-based telescope nor a locked-in-orbit space telescope could be exactly where it needed to be. The first telescope was put on a Convair 990 and was named Galileo, after the famous astronomer. Galileo's eclipse-chasing mission was a success, and did so well that NASA asked itself the age-old question, what if we do a bigger one? This led to the Kuiper Airborne Observatory in 1974, and then SOFIA being proposed as an even larger iteration again in 1996. SOFIA is a technological marvel. Getting a telescope to work on a moving aircraft is about as difficult as spinning a plate on a stick while standing on the roof of a moving car. Don't try this, by the way. SOFIA would need to take images of objects millions to billions of light years away. To do this, it would need to remain perfectly still, even as the plane around it rocks with the wobble of turbulence, the vibrations of its engines, and the rush of wind ripping into the telescope's open cabin. If the telescope vibrated even slightly from any of this, it would be impossible to track the stars and planets it was trying to see. It would repeatedly be supercooled by the low temperatures of high altitude, then warmed again at ground level, potentially leading to cracks and damage to the 8 nanometer precise mirror. An incredible task NASA and German scientists had set for themselves. They solved these problems ingeniously. SOFIA's telescope is set on a series of gyroscopes, magnetic torque motors, and high-speed cameras that allow it to remain perfectly still as the plane around it moves. The door that opens on the side of the airplane comes equipped with an intricately sculpted ramp on one side, tested in wind tunnels to reduce the 850 km/h winds the Boeing flies at to just 80 km an hour. And the mirror itself is built using a ceramic glass composite called Zero Dur that has almost no expansion or contraction under temperature changes. Its equipment is unique in almost all the world. SOFIA is primarily an infrared telescope, but thanks to some additions that were made to its Hawk equipment early on, SOFIA is one of the few telescopes capable of seeing the polarization of dust clouds. This gives SOFIA the incredible ability to see magnetic fields across galaxies. However, with its greater size and sophistication than its smaller forerunner Galileo, SOFIA's costs grew too great for its scientific contributions. SOFIA began its 5-year mission in 2014, and was then given a further 3-year extension. But while in its first 6 years the Hubble telescope was cited in more than 900 scientific papers, SOFIA featured in only 178. This led the National Academics Decadal Survey on Astronomy and Astrophysics in 2020 to conclude that SOFIA did not contribute enough scientific discoveries to justify its high running costs. NASA took their recommendations on board and concluded there was no room for SOFIA in the future of astronomy, seeing as there are likely bigger and more exciting infrared telescopes on the horizon that could better use the funding. So, was SOFIA a quirky idea that went too far? Some in the infrared telescope community would say no. Its productivity was ramping up towards the end of its life, even as NASA decided to cancel it. But ultimately, the value of its existence can only be weighed by its discoveries. Let's examine a few of the biggest so you can decide for yourself. Being an infrared telescope, SOFIA is able to see through thick bands of dust that visible light telescopes would struggle to penetrate. As such, it has been able to capture moments like this one in the Orion Nebula. Here, a young star creates a bubble of space around it by blowing the dust away with its stellar winds in a process known as feedback. It was previously believed that only supernova could do this, so discovering that regular stars did the same has been a key discovery in understanding the formation of stars in the early universe. The stellar winds prevent new stars from forming too close to the current one, while also compressing the dust further out, increasing the chances of stars being created further away. And what about this planetary nebula, NGC 7027? By analyzing its light signature, scientists were able to discover helium hydride in space for the first time. This molecule had long been thought to act as a key building block for more complex chemistry back when the universe was only 100,000 years old. But up until SOFIA spotted it here, scientists had had no proof it actually could be found in space, having only created it in lab conditions. One of many examples of theory outpacing observation. SOFIA's ability to see in infrared gives it insights into the temperature of the universe. For instance, by noticing that the infrared brightness of debris in this double star system was 10% brighter than it had been a decade ago, scientists were able to deduce that 2 large exoplanets had likely violently collided into each other in the system, heating up the matter and dust around them. This cataclysmic collision would otherwise have been very difficult to detect. But my personal favorites of some of the most mesmerizing images are these. These strange lines that you can see weaving through the images of stars here are magnetic fields that channel mass in ways scientists had only dimly perceived up until SOFIA. These fields can allow mass to escape from galaxies, can keep it away from black holes like the one in the center of our Milky Way, keeping it peaceful and quiet, or can funnel mass towards black holes, ensuring they are constantly consuming mass. If you want to know why the universe works the way it does, understanding the role of magnetic attraction is as vital as understanding gravity, and that's something SOFIA gives us like no other telescope. From nebula to planets, from the formation of stars to the fundamental building blocks of the universe, SOFIA has peeled back the curtain to reveal fascinating secrets, and has done so in a way that is truly unique. Men and women have ridden along with it, performing science in real time as it swept its gaze out across the universe. Perhaps it was a relic of a bygone time, and planes are not the true future of space exploration. But without trying things out and innovating, we would never really know. So, what do you think? Was it good that we had SOFIA, even if only to say that it didn't achieve as much as we hoped? Or would the money have been better spent elsewhere? What is the price we can put on experience and knowledge? Either way, for better or worse, for nearly a decade, NASA and German scientists really did try to stick a telescope out the side of an aeroplane. And that is a fact that has expanded my understanding of what is possible.
I'd be surprised if any of you managed to avoid the news last week about the black hole that was imaged at the center of M87, an elliptical galaxy roughly 55 million light years away from us. This mammoth of a black hole is one of the biggest that we know of, with a suspected mass of around 4 billion suns. This makes the supermassive black hole at the center of our own galaxy comparatively puny, Sagittarius A star only being 4 million solar masses. M87's black hole, known as M87 star, is not just massive but also huge. The way we measure a black hole is from its event horizon, or the point in which not even light can escape the black hole's gravity. Just to give you a sense of scale, if our solar system was sitting at the center of M87, the orbit of Neptune wouldn't even come close to the event horizon. It even dwarfs the largest star that we know of, JWST, which is the star in this video by the side of our solar system. So why not use Hubble to image M87's star? It's the best telescope we've got at the moment, right? Well, in some ways, yes, but not all telescopes do the same thing. The Hubble telescope has indeed looked at M87, but Hubble can only see predominantly in visible light wavelengths. This isn't so good for looking through objects, like gas and dust, which blocks the view. That's why Hubble's view of nebula and galaxies looks so impressive. It sees all the dust structures and molecular clouds. Black holes, unsurprisingly, don't produce any light, which makes them extremely difficult candidates to observe. What we can see, though, is the bright material found in a black hole's accretion disk. Still, due to the vast amount of material in a black hole's accretion disk, actually observing a black hole is very difficult in the visible light spectrum. This video shows what the accretion disk of a black hole would look like through different wavelengths of light, starting with shorter wavelengths. As the wavelength decreases, the material surrounding the black hole becomes more visible. So the secret to imaging a black hole is to get the frequency just right, to give a good balance of what's visible. And that's what the Event Horizon Telescope is. It is a huge array of ground-based radio telescopes throughout the world acting in unison to image black holes like this one. An array provides a much bigger aperture, effectively the size of the Earth, as they have synchronized telescopes together from all over the planet to provide a much sharper image than a single telescope could achieve. Although it should be noted that this doesn't make the whole Earth a giant mirror. The light collecting capabilities are only as large as the size of the mirrors collectively used. It's just the aperture that improves. The other major difference between the Event Horizon Telescope and Hubble is the angular resolution it can achieve. Even though M87 star is a mammoth black hole, the distance to it is so vast that the Event Horizon Telescope is effectively looking at the equivalent of a grapefruit on the moon, an object only 30 micro-arc seconds across. Hubble doesn't get anywhere near close to this resolution. In reality, when studying astronomical objects, it is important to use all the frequencies of light, as this provides a much more complete picture of the object in question. For instance, while the Event Horizon Telescope can look closely at the black hole itself, other telescopes can observe the accretion disk, the jet blasting away from the black hole, and the galaxy itself. I think this just leaves one question about imaging black holes. Why did they choose to image M87 star and not the black hole found at the center of our own galaxy, Sagittarius A star? Although it's smaller, it's much closer, so it must be easier, right? Well, the difference is that M87 star is also a lot more active than our black hole, and combined with its giant size, makes it easier to observe. It is thought that roughly 1 solar mass is falling into the black hole from the accretion disk every 10 years, and this jet, blasting away from the black hole for tens of thousands of light years, is testament to this tumultuous activity. On the other hand, Sagittarius A star is very quiet, meaning it is a lot harder to see at the moment, but the Event Horizon Telescope will be having a look at this too, so it won't be long before we can compare the two, hopefully.
Rogue planets are one of the great mysteries left in the universe. They are planetary-sized objects that are not gravitationally bound to a star. We don't fully understand how they formed. Perhaps they formed in a planetary system but got ejected during the system's turbulent beginnings. Following that thought, Perhaps our own solar system also had additional planets at the beginning, before they were cast away to forever roam the galaxy alone. Rogue planets could also be protostars that simply failed to absorb the mass needed to become a star or even a brown dwarf. We expect there to be billions to trillions of them out there in just our galaxy alone. Although, because they are hard to detect, this really is an educated guess at best. However, since the turn of the century, we have started to detect a few of these mysterious objects. How can that be when there are no stars lighting them up, and since they don't emit their own light? If they are pitch black, how do we have any hope of detecting them at all? Well, this is where a very interesting detection technique comes in, called gravitational microlensing. On this channel we have explored various exoplanet hunting techniques in the past, mainly the radial velocity method and the transit method. The radial velocity method measures the wobble of a star caused by the gravity of orbiting exoplanets. The transit method measures the brightness of a star over a long period of time that looks for dips in the star's brightness when an exoplanet passes in front of it. However, these methods are only useful for detecting exoplanets around stars, and generally these exoplanets tend to be large and have very close orbits. The gravitational microlensing method is an exciting method because not only can it find exoplanets much further away from their host stars, but these planets can also be as small as Mars, or possibly even smaller than that, and still be detected. Additionally, rogue planets with no star at all can be detected with this method. Sounds almost too good to be true, but there is one catch. So how does it work? Gravitational lensing is a well-known phenomenon in astronomy and has been used for years to detect some of the most distant galaxies that we know of. Einstein predicted this phenomenon back in 1936, and with the development of telescope technology, it has been confirmed by observation. Basically, the further away a light source is from us, the dimmer it becomes thanks to the inverse square law. The reason objects get dimmer with distance is that photons spread out as they travel, meaning the further away you are from the object, the fewer photons that reach your eyes. However, when there is a body with a large amount of mass, like a galaxy or galaxy cluster, the mass of the object warps the curvature of space-time depending on how massive it is. Light follows the curvature of space-time, meaning that if light emitted by a distant object travels past a massive object, the light photons that would have otherwise gone off in these directions bend back around thanks to the object's gravity, making the background object appear brighter to an observer here than it otherwise would have done, as more light photons are reaching them now. Gravitational lensing is very obvious when we look at the biggest types of objects, galaxy clusters, because these objects warp spacetime the most. This means that if we are aligned just right with a galaxy cluster and a distant galaxy, the distant galaxy would appear much brighter. The light from the distant galaxy bending around the nearer galaxy would also actually make the galaxy appear stretched, sometimes into the form of a ring. You may have seen these Hubble images before, where distant galaxies appear totally distorted thanks to this gravitational lensing effect. And here is a CGI example of what you are seeing, which may help you understand why this happens. Now, as I mentioned, more recently the use of gravitational lensing has also been used to help astronomers detect exoplanets. Stars and planets are much less massive than galaxy clusters, but gravitational lensing still happens to a small degree. When a star transits in front of a distant star, the distant star will become brighter as its light follows the curvature in space-time around the foreground star. Additionally, should the foreground star have an exoplanet or exoplanets, the distant star will also get slightly brighter when these transit in front of the distant star too. This is the process of gravitational microlensing. This process is so accurate that small Earth or Mars-sized exoplanets can be detected, and potentially even large exomoons. Astronomers simply need to measure the little peaks in brightness to distinguish between the individual bodies orbiting the foreground star. Now, as I mentioned, there is a catch with this method, and that is that star transits are actually quite rare, because they really need to be aligned just right from our perspective, and the galaxy is simply huge. There's so much space in between stars. This is why, up until now, the transit method has had a far better success rate at detecting exoplanets, because exoplanets orbit and transit their stars a lot quicker than stars transit other stars. So, in order to spot these events, what we need is to observe a huge swath of sky in one go. Enter the Nancy Grace Roman Space Telescope, previously known as the JWST Observatory. This telescope, due to be launched in 2025, is comparable in size and will provide images with a sharpness similar to the Hubble Space Telescope, except the Roman Space Telescope will be equipped with a 288 megapixel camera and a 0.28 square degree field of view, which is 100 times larger than Hubble. With this field of view, it will be able to keep track of a much larger section of the sky and monitor for microlensing events. How does this all fit in with rogue planets? Well, much like stars, rogue planets that transit in front of a distant star will also make that star slightly brighter. And if the Roman Space Telescope is looking at that section of the sky, it should be able to detect it. In fact, throughout its 5-year initial mission, scientists hope that the Roman Space Telescope can give us a much better indication of how many rogue planets and Earth-sized exoplanets there are out there. Now, while it is possible that rogue planets are in any section of the sky, the Roman Space Telescope will focus its time looking towards the center of our galaxy. There are a lot more stars here, so transit should be more frequent, and this will increase the chances of spotting microlensing events. It is amazing to me that there are ways to detect these otherwise invisible objects that emit no light, and all you need to do is look at the brightness of a background star, and as a rogue planet passes in front of it, the gravitational microlensing event will reveal key details about the rogue planet, like its mass. So, have we detected any rogue planets this way at all? As it happens, yes we have. There are a few ground-based programs on the hunt for rogue planets operating right now, like Ogle, Moa, and Supermacho. At present, they have found 22 rogue planet candidates in all, with the most exciting one being Ogle 2012 BLG 1323. If this rogue planet gets confirmed, it will be the smallest rogue planet discovered by some ways, being roughly the mass of Earth. How a body like this comes to be free floating in space, we don't really know yet. We're still really early in this field of discovery. But as the James Webb Space Telescope and the Roman Space Telescope launch, hopefully we'll uncover much more information about these fascinating objects. So there we have it, how we can detect the invisible objects that are rogue planets. If I tell you to imagine a telescope, what do you see? Perhaps you picture an old wooden cylinder with lenses at both ends, similar to the one that Galileo Galilei first used to gaze up at the heavens and see the moons of Jupiter. Or maybe your mind is constructing a cathedral-sized dome with mirrors as big as tennis courts, like the telescopes high up in the mountains of Chile and Hawaii. Or you could even be drifting onto visions of enormous dishes, like the infamous Arecibo telescope that once captured radio waves from across the cosmos. What you probably aren't imagining is a cubic kilometer of ancient ice under the surface of our planet's South Pole. And yet, deep below the frigid landscape of Antarctica, there lies precisely this. A strange telescope in one of the most inhospitable environments on Earth, designed to observe, not visible light, but instead one of the most unusual and elusive particles in the universe. I'm Alex McColgan and you're watching Astrum, and today we're joining the IceCube Observatory in its hunt for neutrinos, also known as ghost particles. If you stood on this icy surface, you might not be aware that some of the rarest events in the universe are being observed beneath your feet. Located at the most southerly human-occupied base in the world, the Amundsen Scott South Pole Station, IceCube makes use of the very ice in which it is built to observe high-energy neutrino particles. But why? Why this extreme environment and weird design? Because neutrinos are weird. Really weird. Neutrinos are fundamental particles like quarks and electrons. Most of these neutrinos arrive at Earth from the Sun, where they are released from the nuclear fusion reactions raging inside its core. Other neutrinos will have come from more cataclysmic origins, such as a supermassive black hole, supernovae, or any other cosmic event with enough energy to rip atoms into their subatomic particles. Similar to electrons, neutrinos belong to the lepton family of particles, meaning that they do not interact with other matter through the strong nuclear force that binds other subatomic particles like protons and neutrons together. Unlike electrons, they are neutral and have almost no mass whatsoever. This lack of charge and tiny mass means that they can only interact with other particles through the weak nuclear force, giving them their ghostly quality and making them one of the most difficult particles for scientists to detect. So much so that even when we do measure their presence, it is only through the impact they have on other particles. If that wasn't spooky enough, neutrinos can also pass through our entire planet without acknowledging the existence of a single atom in the crust, mantle, core, or any other layer of the Earth, flying straight out of the other side completely unnoticed. There are trillions of neutrinos surging through you every single second, and yet, over your entire lifetime, there is only a 1 in 4 chance that even one of those neutrinos will interact with an atom that belongs to your body. Here we find further demonstration of the neutrino's complete refusal to engage with matter in the universe. Photons, created in those same nuclear reactions, may take 1 million years between bursting out of the sun's center to leaping off the surface into space. They are constantly absorbed and emitted in random directions over and over again by the atoms in our star, resulting in a long, meandering path to escape. Neutrinos instead zoom straight out of the sun in just 2 seconds, traveling at almost the speed of light itself. As far as standard model particles go, neutrinos are certainly the more coy and antisocial of the group, but on occasion they do mingle with other matter, and in the process can create a drama of energetic particle events cascading out in their wake. It is this cascade IceCube is trying to observe. They might seem strange, but the 5,160 detectors, or DOMs, suspended down between 1.5 and 2.5 kilometers in the darkness of the ice shelf, are in fact light detectors. The sun's rays have of course been completely swallowed up by the thousands of meters of compressed ice that lie above, but that doesn't mean there is no light at all down here. Neutrinos and cosmic rays can penetrate into the ice, and when they collide with the atoms of frozen water, they cause particles, like muons, to spring into existence. Muons are the key to identifying a neutrino interaction. As the newly created muon hurtles through the incredibly clear and dense ice, it can exceed the speed it takes light to move through that same ice. Now, let's be clear, nothing can move faster than light in a vacuum, but in other materials such as ice, liquid water, and glass, light can be outpaced. This isn't a violation of physics, but rather a consequence of light slowing down more than other particles within the ice. As the muon races beyond its photon counterparts, it generates a shock wave of blue light expanding in a cone-shaped pattern out from its path, an eerie phenomenon known as Cherenkov radiation. Cherenkov radiation is most commonly associated with nuclear reactors. eerily emanating through the water that surrounds their cores. This blue hue in nuclear cores, and strangely also down in the ice of the South Pole, can look peaceful and atmospheric, but it is in fact the quantum equivalent of the sonic boom that roars out from a supersonic jet plane flying overhead. In this case, the plane moves through the air and pressure or sound waves are pushed out in all directions. With the jet's speed building up towards the speed of sound, the waves in front start to bunch up, forming a shock front of high pressure. When the plane exceeds the speed of sound, it smashes through the shock front, causing a rapid change of air pressure. This is the sonic boom. The shock front then travels out in a cone, trailing behind the aircraft, which observers will hear as a thunderous clap. In the case of the muon, the particle is not pushing air, but instead disturbing the electric fields of atoms in the ice with its electromagnetic charge, polarizing the water molecules. As the molecules depolarize back to their usual state, they release the energy that forced them into polarization as photons of blue light traveling out in all directions. This is happening all along the path the muon takes through the ice. The traveling muon is triggering emission of electromagnetic waves from the water ice molecules, which radiate out into all directions, producing a cone of emission in the direction of the muon's motion. If the muon was traveling slower than light in the ice, there would be no wavefront, and all the expanding light spheres would destructively interfere with each other, cancelling out to complete darkness. But since the muon is traveling faster than light, the shock front of constructive waves in the form of blue light is created. The thousands of digital optical modules of IceCube are primed to detect this signature blue light flashing through the ice. The minuscule differences between when one DOM registers the flash and when the neighboring DOMs detect it allow scientists to triangulate the neutrino and trace its path back through the ice and ultimately through the universe to its origin. These orb-like detectors are marvelous, intricate devices designed to detect the faintest luminal hints in the icy mass. Each DOM is encased in a 13-inch spherical glass pressure case, which protects the electronics inside from the extreme cold and high pressure of the Antarctic ice. Inside, there is a photomultiplier tube sensitive enough to detect even a single photon, along with various components that amplify the signal and convert it into digital data, which is then transmitted up the cables to the surface. And with so many detectors making up this three-dimensional array, there is a lot of data. A whole terabyte of measurements are captured every day, with hundreds of gigabytes of that being beamed by satellite to scientists across the planet for them to comb through in search of their ghostly quantum target. Within this trove of data lie the imprints of many particles arriving from beyond our atmosphere. The vast majority are cosmic rays. IceCube detects around 275 million of them daily. Cosmic rays are interesting in their own right, but serve as an obscuring curtain of noise to those seeking neutrino interactions, which occur a million times less frequently, with only around 275 detected daily. But even with the 100,000 neutrino detections that IceCube makes each year, almost all of them are generated in our own atmosphere as debris from collisions of cosmic rays with atoms in the gas that surrounds our planet, and not from cosmic origins themselves. The keyword here being almost. On the 22nd of September 2017, an exceptionally bright burst of Cherenkov radiation was registered by IceCube's array of detectors. Working together, the DOMs used the tiny time differences between when they each detected the flash to trace the path of the muon and the exceptionally energetic neutrino that created it, all the way back to a powerful and mysterious cosmic source out in the depths of our universe, a blazar, a supermassive black hole at the center of a distant galaxy, hurling jets of particles towards Earth. This discovery was monumental. It was not the first time that IceCube had detected neutrinos from deep, deep space. but this detection was the first to trigger a real-time alert to telescopes across the globe, indicating that there was something significant to look at in that direction. IceCube and neutrinos had entered the world of multi-messenger astronomy, where the cosmos is studied through not just light, like it has been for most of the history of astronomy, but also gravitational waves, cosmic rays, and now neutrinos. Neutrinos are a particularly useful window for us to look through because, like gravitational waves, they can arrive at us before the light from a major astronomical event does. Because of their ghostly nature that I talked about before, neutrinos take a very direct path to our detector, whereas light faces many obstacles like dust and magnetic fields that interfere with its journey and slow it down. IceCube is now fully integrated into a planetary network of observatories, constantly scouring the skies for signs of high energy events, ready to inform radio dishes, mirrors, and lenses precisely where to point to see rare and transient phenomena that we would otherwise miss completely. IceCube is the noble watchman, sounding the alarm to rally an army of telescopic troops across the globe, commanding them where to aim to catch sight of raging cosmic fires. And even further to that, IceCube can give us a unique view into the heart of these phenomena. Because again, unlike photons, neutrinos can escape relatively unscathed from high energy environments such as the core collapse of supernova explosions or cataclysmic mergers of unfathomably dense neutron stars, or even the searing fury of supermassive black holes. IceCube can deliver new and different information. It can see things light-based telescopes are blind to, so to speak. The neutrinos it detects can hugely broaden our understanding of all these events and of the most fundamental nature of the universe. During these events, physics is pushed to its limits. Particles are accelerated to speeds and energies thousands of times greater than what we can achieve in our particle accelerators on Earth, like that of CERN. This allows physicists to test their theories and use the arrival of neutrinos at IceCube to make new discoveries, not only about the behavior and properties of neutrinos, but also about dark matter and even about ice itself. This is why so much effort was put into building such an extreme telescope as the IceCube Neutrino Observatory, an effort that took 7 years to complete, with work pausing during the Antarctic winter when planes are shut out from Earth's most southerly continent by the brutal weather, only able to briefly resume for the summer months of November to February. Over those 7 years, the IceCube team drilled 86 holes 2.5 kilometers deep, using 18,000 liters of fuel per pole and melting 750,000 liters of ice in the process. All to have a few hundred scientists live and work in one of the most inhospitable environments on our planet in an attempt to understand the most extreme events in our universe and to capture a glimpse of the most elusive particle in the universe. Neutrinos are the phantoms of the particle kingdom. It takes bold and ingenious ideas from ambitious scientists to witness even a single one neutrino. We know so little about them compared to other particles, but they are just as important in furthering our understanding of the fundamental laws of nature. With each neutrino detected, we are moving closer to comprehending the universe and the powerful forces that shaped it. Thanks for watching. This video was in part made possible by all the astronauts on Patreon. If you think these videos add some educational value to the world and want to give them more stability than the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Just sign up with the link in the description. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.